Right, grade 12, as you can see, we are looking at matter and materials, module 2, unit 2, optical phenomena and properties of materials. This is our second last unit for the year. We sometimes talk about this unit as just the photoelectric effect because that's what we are going to be dealing with in this unit. Just some quick revision from previous years. We can see here we're looking at electromagnetic radiation. We can see there's various forms of electromagnetic radiation. We have at the very low frequency and long wavelength at the end, we've got long radio waves and other types of radio waves, then microwaves. Then we have infrared. We've heard of infrared before. That's the radiation that any warm object radiates. And then that little rainbow in the middle, that is our visible spectrum. So that's visible light. That's the light that our retinas are able to pick up. As our frequencies increase, we then move on to our UV light, as we can see there, then X-rays, and then finally the electromagnetic radiation with the highest frequency is going to be gamma rays. Now, the frequency increases as I move towards the left, and as I move towards the right, the wavelength increases. The way that this works is that they are inversely proportional. As I get if I have a wave with a higher frequency, remember then those waves must be, the peaks and crests must be closer together, so obviously my wavelength gets shorter. If I've got a lower frequency, then the wave is stretched out more, so therefore it's got a longer wavelength. Now, electromagnetic radiation has a dual nature. We have the wave model and the particle model. With the photoelectric effect, that is a case where the particle nature or the particle model of light is most visible. So this is where light acts more as a particle as opposed to a wave. But we remember, of course, we continue using frequency and wavelength as well. Just to recap, if my frequency of my wave is higher, then the wavelength is shorter. If the wavelength of the wave is longer, the frequency is going to be lower. What is the photoelectric effect? We can see it's the process whereby electrons are ejected from a metal surface when light of suitable frequency is incident on that surface. So if a photon, remember photon is a packet of light energy, if it's got enough energy and it strikes a metal surface, then electrons from that metal surface are released. This only happens if the photon has sufficient energy, and the energy of a photon depends on its frequency. We can see there for the threshold frequency, that's the minimum frequency of light needed to emit electrons from a certain metal surface. Whether an electron is released from a metal surface or not only depends on the energy, thus the frequency of the photon. It doesn't matter how many photons, in other words, how intense the light is, that does not matter. Even if I've got millions and millions and millions of photons striking the metal, if their frequency is lower than the threshold frequency, no electrons are going to be released. The photons need to have sufficient energy in order for electrons to be released. So in summary, there's a threshold frequency below which no electrons is released. So if I shine a light with a lower frequency than the threshold frequency, no electrons are going to be released from the metal surface. Electrons are released at a rate proportional to the intensity of light. What that means is that if the photons do have enough energy or a high enough frequency, then the more photons I shoot on that or project onto that metal, more electrons are going to be released, or they're going to be released at a greater rate. This can increase my the current that I can experience. Then the energy of the emitted electrons is independent of the intensity of the incident radiation. So the electrons are going to have an energy, but that is only tied to the energy of the photons. Again, not how many photons strike the surface. And this is again why we say that here we look at the particle nature of light. Then if we look at Einstein's photon model of light, light consists out of these small packets of energy called photons, and each photon carries a quantum or an amount of energy which is dependent on its frequency. we can see the energy is equal to h, that's Planck's constant. If we have a look here quickly, Planck's constant is always given in your as one of your constants in your data sheet. Here we can see h is equal to 6,63 times 10 to the power of minus 34 joules second. All right. So if we keep that in mind, the energy of a photon is the product of Planck's constant and its frequency. Therefore, its energy is not influenced with the intensity of light. It's only influenced with its frequency. So if we go back to our second slide where we have our electromagnetic spectrum, the higher my frequency, so the more I lie towards the left on the scale, the higher energy the photons of that type of radiation is going to have. As I move towards the right, the frequency decreases and thus the energy decreases also. Then we can just see here, I can rewrite HF, so Planck's constant times the frequency, as hc over lambda. Now, c is just a constant. It's the speed of light through a vacuum, and that's 3 times 10 to the power of 8 meters per second. That is also given on your data sheet. And then lambda, all right, that is going to be the wavelength of the light. So we can see that as wavelength increases, it's a denominator, my energy is going to decrease. As wavelength decreases, energy is going to increase. So energy of the photon and wavelength are inversely proportional to one another, whilst the energy of a photon and its frequency are directly proportional to each other. And this speed of light is equal to the frequency times the wavelength. So this allows me that if I give you the wavelength of a certain type of radiation, then you can substitute in your C, the 3 times 10 to the power of 8, and your wavelength, and then you can calculate your frequency. Then we've got another definition here for the work function. Now, the work function of a metal is the minimum energy needed to eject an electron from the metal surface. In other words, if a photon strikes a metal with an energy lower than the metal's work function, no electrons are going to be released. It doesn't matter how intense the light is, how bright the light is, that's what intensity is. No electrons are going to be released if the energy of the photons are below or is below the work function of the metal. And the work function will have to be given to you. All right, we'll show you now. Alternatively, we can give you the threshold frequency or the threshold wavelength. Then your most important equations are these two at the bottom. And it basically what it does is it tells you if a photon with a certain energy strikes a metal, how much energy will an electron have when it is released? Because remember, when the energy of the photon is greater than the work function, then an electron is going to be released from the surface of the metal. So the energy of the photon is equal to the sum of the work function, which is fixed, plus the maximum kinetic energy of the what we call the photoelectron, or the electron that has been released or ejected from the metallic surface. I can just rewrite this using the equations at the top. Instead of E for the photon, I just write HF, that's Planck's constant multiplied with the frequency of the photon. That's equal to the work function plus a half times mv squared max. And that a half mv squared max, that's just kinetic energy, isn't it? A half times mass times velocity squared. And the mass there is the mass of an electron. That again is given in your as one of your constants. We'll see here electron mass, that's me or m subscript e, that's 9,11 times 10 to the power of minus 31 kilograms. A very, very, very small mass, as you can see there. So this equation allows you to then determine what the maximum velocity or the maximum kinetic energy of an electron is going to be when a suitable light is shone on that metal. We're going to look at an example of this in a moment. Before we go on, we've just got two more definitions, the cutoff frequency and the cutoff wavelength. The cutoff frequency is very much like, it's numerically the same as my threshold frequency. We can see it's the frequency of light which will emit photoelectrons with a zero kinetic energy. In other words, if my frequency is lower than the cutoff frequency, then no electrons are going to be released. The cutoff wavelength is the wavelength of light which will emit photoelectrons with zero kinetic energy. And then if we compare that, then we're just making my kinetic energy zero, and then my E photon is just equal to HF. So I can say then that my work function I can also find by saying H times my cutoff frequency, or HC over my cutoff wavelength. We're going to be able to see that in a moment. So that's another way of calculating my cutoff or my work function if that is not given to me. All right, just to go through this again. The higher the frequency of the photon, the more it lies towards the right, and thus it has more energy. All right, because energy, as we said, is just Planck's constant multiplied with my frequency. If I've got a lower frequency, then HF is going to be smaller, so the energy of my photon is going to be smaller as well. And then my wavelength just works the opposite way to that. If I've got a shorter wavelength, I've got a higher frequency and thus a higher energy for the photon. If I've got a longer wavelength, my frequency is lower, therefore I've got a lower energy for that photon. We can see here with my visible light as well, my wavelength increases as I move towards the red side and decreases as I go towards the violet side. So red light has a longer wavelength, thus a lower frequency and thus a lower energy, whereas violet light has got a shorter wavelength, therefore a higher energy, and thus also a higher frequency and thus also a higher energy. So we can say energy of a photon is directly proportional to its frequency, whereas energy of a photon is inversely proportional to the wavelength of the light or of the electromagnetic radiation. And all of these are just different types of light, whether we're looking at gamma rays or X-rays or ultraviolet rays. Remember, that's the light that is also emitted by the sun, which can cause sunburn. All of these are higher energy light, so they are more dangerous also to human beings because they've got that higher frequency and there's higher energy as well. All right, we're going to have a look at a past paper question now. We can see we've now, in the previous lesson, we had a look at question 10, which was our electromotive force or our electrodynamics. Now we're looking at question 11. This is usually going to be the case for our photoelectric type of question. And they say here that the threshold frequencies of cesium and potassium metals are given in the table below. Both of those are metals. They don't give us the work function here, they give us the threshold frequency. So that is, if we go back, what's our threshold frequency? We said our threshold frequency is the minimum frequency of light needed to emit electrons from a certain metal surface. And as you can see, both of these have two different threshold frequencies. The higher the frequency, that means more energy is required to release that electron. And if I shine a light, say for instance on cesium with a frequency lower than 5,07 times 10 to the power of 14 hertz, then no electrons are going to be emitted. But if it's higher, if the light has a frequency higher than the threshold frequency, then electrons will be emitted. All right, 11.1 definition. They say define the term work function in words. We've done that already. And work function of a metal is the minimum energy needed to eject an electron from the metal surface. Just note here, if any of the underlined keywords or phrases in the correct context is omitted, deduct 1 mark. So be careful, make sure you've got that definition just as it is there. What is the work function? The work function of a metal is the minimum energy needed to eject an electron from the metal surface. All right, let's go on. They say, which one of the two metals in the table has the higher work function? Give a reason for the answer by referring to the information in the table. So if we go back quickly to our work function, we saw that my work function, I can say that's h times the threshold or cutoff frequency. So h times f0. So which one's got the highest cutoff frequency? And we can see that potassium has the higher threshold or cutoff frequency. Therefore, it is going to have the higher work function, because we can see work function is just equal to h times the cutoff frequency, or h times the threshold frequency. H is of course a constant. So we can see then, if we have a look at our solutions, potassium is going to have the higher work function, and that's because the cutoff or threshold frequency for potassium is greater than the cutoff frequency for cesium. You can also say there that work function is equal to h times my cutoff frequency, or h times f0. You can also say there that work function is directly proportional to the threshold frequency, and since potassium has a higher threshold frequency, it's going to have the higher work function also. All right. Then we go on. They say the simplified diagrams below show two circuits, A and B, containing photocells. Now a photocell, as you can see there, you've got the metal, you've got a glass tube surrounding that metal, and then there's another electrode on the other side. And when light shines on that and it's above my threshold frequency, light is going to leave my metal plate and it's going to jump over to the other electrode, thus completing the circuit. And I can then measure the effectiveness of this of the photoelectric effect just by using an ammeter, because remember, an ammeter just measures the rate at which charge flows through it. So if electrons are ejected from the cesium metal plate, they go and they land on the other electrode, and then they continue moving through the circle, and this process continues, and thus I've got current or charge moving through my ammeter, so it's going to give me a reading. Now the photocell in circuit A contains a cesium metal plate. All right, we've seen that already. And while the photocell in circuit B contains a potassium metal plate. Ultraviolet light, that's light with a relatively high frequency, with the same intensity and wavelength of 5,5 times 10 to the power of -7 meters, is incident. What does that word mean? Incident just means it shone on the metal plate. Incident on the metal plate in each of the photocells, and the ammeter in circuit A registers a current. What does that mean? It means the photoelectric effect is taking place. Electrons are being ejected from the cesium plate, they're landing on the other electrode, and the circuit is completed. So the photoelectric effect is definitely taking place for cesium. Then they say in 11.3, by means of a calculation, determine whether the ammeter in circuit B will also register a current. So ultraviolet light is shone on the potassium plate, but I don't know whether or not electrons are going to be emitted. All I know is that the wavelength of the ultraviolet light is 5,5 times 10 to the power of -7 meters. I also know that potassium needs a frequency of light of 5,55 times 10 to the power of 14 hertz. So what this forces me to do is I have to determine, is this light, this ultraviolet light with the 5,5 times 10 to the power of -7 meter wavelength, is that a higher or lower frequency than my threshold frequency? If it's higher than my threshold frequency, photoelectrons will be emitted. If it's lower than my threshold frequency, electrons are not going to be emitted. So I basically have to convert this wavelength to a frequency. Let's see what they do there. This is 11.3. We're just looking at option 1. We say here the speed of light is the product of the frequency and the wavelength. I know what the speed of light is. It's 3 times 10 to the power of 8. I say that's equal to f times lambda. That's my wavelength. And then I find that my frequency of the ultraviolet light is 5,45 times 10 to the power of 14 hertz. Therefore, the frequency of the UV light is less than my threshold or my cutoff frequency for potassium. So therefore, there's no photoelectric effect is going to take place. No electrons are ejected or released from the metal plate. So no electrons jump over to the other electrode. So no ammeter reading is going to, I'm not going to see an ammeter reading. I'm going to see an ammeter reading of 0. So therefore, we can see ammeter in circuit B will not show a reading. All right. Again, why is that? Because the frequency of the UV light, which I've calculated using C equals F times lambda, is lower than the threshold frequency for potassium. And remember, the threshold frequency for potassium, that's the minimum frequency I need in order for electrons to be emitted or ejected. So have a look at 11.4. They say calculate the maximum kinetic energy of an ejected electron in circuit A. So remember, in circuit A, they said I do have an ammeter reading, so photoelectrons are going to be ejected, electrons are going to be ejected. I just now need to see what my maximum kinetic energy is going to be. So we go back here. If we have a look at my equations here, the energy of a photon is equal to the work function plus the Ke max. The Ke max, the maximum kinetic energy, that's what I want. So I need the energy of my photon and I need the work function. All right, so I'm going to use one of these equations. I can also, like always, I can rewrite energy of the photon as hc over lambda. I might need that because, as you saw, we just have the wavelength of the UV light. We don't know yet what its frequency, or we did actually, yeah, we don't know what its frequency is. Now we did calculate that in the previous question, so we can use that. So we can use this equation here. I will just need to also calculate the work function for the cesium, and work function always I can find that by just saying it's h times the cutoff or threshold frequency. So let's see what they do here. We can see we can use any of those three equations. I like to just start with this basic equation here, E equals work function plus Ek max, and then I just start substituting in here. And we can see they've basically used hc over lambda for the energy of the photon of ultraviolet light, and then your work function is Planck's constant multiplied with the frequency of, or the cutoff frequency, which was given in the question, and then Ek max, that's what I want to solve. So I substitute in Planck's constant, always 6,63 times 10 to the power of minus 34. C, speed of light through a vacuum, is 3 times 10 to the power of 8. And then this 5,5 times 10 to the power of minus 7, remember, that is the frequency of the ultraviolet light that they give us. So I substitute that in. That's the energy of the photon that's coming towards the cesium plate. Then that energy is split up into my work function and my Ek max. You can think of the work function as it takes some of the energy of the photon, and then the remainder is given as kinetic energy to my electron. The work function is the energy required just to break the electron free, and then the remainder of the energy gives the electron kinetic energy. It makes it go faster or slower. So we can see I've just put Planck's constant in here again, multiplied with the threshold frequency, which, as I've mentioned, that one was given to you in the table for cesium 5,07 times 10 to the power of 14. I substitute that in. I basically subtract this term here, the h times the threshold frequency from both sides, and I get Ek max equals 2,55 times 10 to the power of minus 20 joules. So very small energy, but that's going to be the maximum kinetic energy that a ejected electron is going to have for that frequency or wavelength of ultraviolet light. We can see then in 11.5, how will the maximum kinetic energy of the ejected electron calculated in question 11.4 change when the intensity of the incident light increases? Choose from increases, decreases, or remains the same. Well, intensity of the incident light increases. Is that going to change the energy of my photon? No, it is not. Remember here, if we look here, the energy is just h times the frequency, or hc over lambda. The frequency, the energy of the ultraviolet light stays the same. Work function stays the same, so my kinetic energy will have to stay the same as well. The only thing, so we choose here that it remains the same. As we can see here, we just say remains the same. The only thing that my intensity can change is it can increase my ammeter reading if electrons are already ejected. And the way that that works is that if electrons are already ejected, if I'm shining a light with a greater intensity, then more photons are striking the cesium plate, and then more electrons are being ejected. That's if that light has a sufficient frequency, if its frequency is above the threshold frequency already. And when more electrons are ejected, then more electrons are passing through the ammeter, so the ammeter reading will increase when intensity increases. The ammeter reading will also, of course, increase if I use a higher energy ultraviolet light source. But the kinetic energy of my particles, or of my electrons, the kinetic energy is not going to be influenced by the intensity. Intensity can only change my ammeter reading. It cannot release electrons with a bigger speed. It can just release more electrons at the same time. All right, so we can see very clearly here that my answer is going to be remains the same. The kinetic energy of my ejected electron is going to, or maximum kinetic energy of my ejected electron is going to remain the same. All right. I hope that that's clear to everyone. In the next lesson, we're going to talk about emission and absorption spectrum. And then later on this week, we will start looking at our last chemistry module, which is going to be electrochemistry. All right. Have a good day.